Allora, salutiamo Enrico, non sbaglio il cognome Pozzobon, stavolta avevo detto Pizzobon, ieri invece Pozzobon. Il titolo dell'intervento è Reverse Engineering of the TriCore Aurix Debug Protocol. Grazie Enrico.
Okay.
Vediamo, aspetta, eccoci.
There you go. Okay. Yeah. Yeah. This is going to be a talk about reverse engineering the TriCore Aurix debug protocol. Before we had the talk, the first talk of the day was also introducing the idea of debug protocols and why they are important for security and for forensics. So this is, I would say, a continuation of that in a way. So first of all, who am I? So yeah, I'm Enrico. I've been working for 9 years in automotive security, so automotive cyber security. I'm one of the founders of this sector. It's a company I founded in Germany, where I live, and where I work as a hardware penetration tester and also hardware developer. Yeah, fault injection is one of my main focuses, and the context of the work that I will be talking about today was a hardware penetration test of an electronic control unit from a car, from a German car, where we were tasked to attempt using side channel attacks and fault injection to break the security of this control unit. Yeah, the target was the microcontroller here, the TriCore, and TriCore is an extremely popular architecture in the automotive sector. You probably never heard of it because it's never used outside of the automotive sector. Yeah, hardware attacks can be used both by the customer to bypass some security check, for example, to do engine tuning, which is interesting for the user, for the driver of the car, but they can also be used by thieves to program new keys in the immobilizer to be able to steal a car. So yeah, these type of attacks are both useful for the users and for thieves. And also, yeah, the typical targets for these hardware attacks are either to extract some secret key, to alter the program flow, so for example to run our own software that we transfer to the microcontroller. But these are very technical attacks and they require a lot of research into one specific control unit. The third typical target here is to unlock the OCD interfaces or on-chip debug interfaces. If you have a hardware attack that is able to unlock a debug interface on one microcontroller, then you can open every microcontroller from that manufacturer pretty much, or at least from that family of microcontrollers. So the target for this investigation was this TriCore Aurix TC397 microcontroller. You see here, this is in the fault injection setup. It's very similar to what you saw before in the first talk of the day. It's an electromagnetic fault injection setup where we have on the top the fault injection head, and we have a development board in this case. It's not the real ECU. We were testing on a development board first. And yeah, the target is these Aurix microcontrollers. They are manufactured by Infineon. They are a pretty recent generation of these TriCore processors. They are real-time microcontrollers. They have up to 6 cores, despite the name. They have like the biggest version has 6 cores plus an HSM, which is an additional core. And as I was mentioning before, they're mostly or only used in cars and bikes. They can be used either for engine control units, gateways, body control modules, immobilizers. They are used all over the place. And here we have 3 examples of ECUs that you might have in your car that run the TriCore microcontroller. As I was mentioning, this is a talk about on-chip debug, OCD. What is OCD? Sometimes you might call it JTAG, but JTAG is only one of the possible protocols that can be used for debugging a chip. It's a on-chip debug basically grants full control of the processor. You can consider it the equivalent of root in the hardware world, or admin power in the hardware world. And it's useful for debugging because just like you have a debugger on your PC to debug individual programs, you can use a debugger connected over an on-chip debug protocol to debug an application that is running on a microcontroller. JTAG is often used as a physical layer. However, it's not the only protocol that can be used for on-chip debug. And on top of JTAG, there are additional protocols that are proprietary for every manufacturer. So for example, we have SVD on ARM. Sorry, SVD is a completely different protocol, but it's used on ARM. We have Nexus on PowerPC processors from Freescale. And we have a DAP from TriCore, on TriCore processors. This is a protocol made, it's a proprietary protocol from Infineon. Now the difference here is that while the first 2 are completely publicly documented and you will find all of the documentation that you want, the DAP protocol is completely hidden. You don't have any information about it. When you open the manual, the only thing they tell you is, yeah, go purchase a Lauterbach debugger, which is an extremely expensive tool. One more thing, these debug interfaces typically can be locked or censored with a password when a device is in field. You don't want to completely disable an OCD protocol because imagine your car enters an accident and it crashes. You might want to be able to do forensics on that car, so you want to be able to unlock the debug interface to be able to extract all of the data. So this is one legitimate reason to unlock the debug interface. And in this case, you can ask for the password to the manufacturer. And they might give it to the police, but they might not give it to you. So JTAG, as I was saying, is a completely standard protocol. Everybody knows about it. I just have a picture here of what you will find on Wikipedia. JTAG defines how to move through the state machine and how to send the data into the data register and the instruction register. And by manipulating those 2, you can then access all of the layers that are on top of JTAG, which are normally documented in the manual of your processor, unless it's a TriCore. And usually a debug interface, a debug setup for a microcontroller looks like this. You have your IDE, where you want to step through the code with your debugger. Then you have a GDB server, or a GDB stub, which your IDE connects to debug a remote target. This then connects to a physical debug interface, usually with USB. And then this debug interface connects with some wires, probably over JTAG, to the target device. And yeah, we saw also before that OCD fault injection is a thing. We can try to record how the power usage of a device looks like when JTAG is locked and when it is unlocked. We can compare the 2 and we can find a place where the lock is established, and then we can try to inject a fault precisely at that time. And of course, this requires very good timing. This is a picture from a very, very interesting paper, Security Different from Safety, from Niels and Ramiro from 2017. I recommend you read it if you want to understand more about fault injection on debug interfaces. Now let's finally come to the actual target of this reverse engineering project, the Debug Access Port protocol. It's the OCD protocol for the TriCore processors, and it is no documentation available. It's supported by proprietary hardware. The official Infineon tools used to only run on Windows. This is actually wrong now because they very recently, relatively recently released the tools, some tools for Linux, but they are still proprietary. You cannot really script them very well. You can't do quick operations that you need for to perform hardware attacks. And I was talking with other automotive penetration testers, and they always told me that they hate how closed this protocol is, and they also wanted something to be published about it. So here we go. So what is already known about the DAP protocol? There are a bunch of points that you can find if you look at published the features of DAP. It's a two-wire protocol, we know that. There are also variants of it which work just with one wire or with 3 wires, but the most common one is the 2-wire version. It's a telegram-based protocol, as in it uses messages, and these telegrams are protected by CRC error detection, specifically with CRC6. And the polynomial is also known. So this is some information that is already known, but it, not really useful. We don't know the meaning of the individual telegrams. So let's try to figure it out with a black box approach, where we just look at the protocol on the wire and see if we can figure it out. We have a choice of where to sniff. This is the same picture we saw before, just with the, let's say, proprietary tools from Infineon. We can sniff in different positions. We could sniff the TCP connection here between the, let's say, tool and the debug server. But this is very easy, of course, but it's not really useful because we are still going to be dependent on this server, which is not optimal. We would like to be able to do our operations as close to the hardware as possible. And we don't want to depend on some tool that might slow us down. We could sniff on the USB protocol. It uses the FTDI MPSSE, which is a protocol used for communicating raw pins, so raw GPIO data over USB. On the Mini Wiggler, which is the proprietary interface by Infineon. Or we could sniff on the two pins of the DAP interface itself with a logic analyzer. And if we look at this application kit that I was working with, this development board, we can see that actually the Mini Wiggler, so the debug interface, is integrated in the development board, and the schematics of this application kit are also published, so we can know exactly where to poke to find the DAP pins. And in particular, they are DAP 0 and DAP 1 here. So we can find them on the correct connector. We can use a logic analyzer, cheap logic analyzer from Amazon, only 10 euros, not sponsored. But it's we can record what the wires look like while I do some debug operation with my debugger on Windows. And we can see that DAP1 is sampled on the falling edges of DAP0. So DAP0 is the clock here. You can see every time there is some data, it's moving up and down very quickly and very regularly with a fixed frequency. And then the DAP1, so where the data actually is, it only changes when on the rising edge of the clock. So we know that the data is sampled on the falling edge of the clock. So out of this, we can figure out that, okay, there is a bunch of bits on the wire, and the bits are sampled on the falling edge of this clock signal, but we are missing an important thing here, which is the direction. We don't know which direction these bits are going. And yeah, this is very annoying because we want to know which bits are sent by the debugger and which bits are responses sent by the device. So let's try another approach here. Let's try to use USB. We have a USB pickup, which is a program which generates pickup files that you can then open with Wireshark. So just the same way you will sniff a network, you can also sniff your USB bus. And the pickup files can then be easily examined and decoded with SCAPI, for example, which usually is for decoding network protocols, but also supports USB. And the problem with this approach is that we get the USB data, but we also have to decode the MPSSE layer, which the GPIO data is placed into. But at least we get to see the direction of the data. So let's do this parsing. There is a bunch of protocols to parse. Of course, first we have the USB. We can parse it with SCAPI because it's just a pickup file. Then we have to parse the MPSSE commands in this protocol defined in the data sheets of this chip from FTDI. Then we will get the bits on the wire, but this time with direction. And then there will be some unknown DAP layers, proprietary. And finally, on top, we should find the debug operations that we are clicking on the debugger, such as run, pause, create a breakpoint, write memory. So the first step, MPSSE, Multi-Protocol Synchronous Serial Engine. It's a protocol found on these FTDI chips. They are extremely popular for all types of debug interfaces and also serial interfaces. For sure, if you work with hardware or microcontrollers, you for sure will have worked with an FTDI chip. They support this protocol, which is very versatile. Normally, it's used for JTAG, SPI, I2C. And here, it's also used for DAP. It's very well documented, so parsing it is not a problem. Here, we have an example of how this step looks like. We have in blue the packets that are sent as an output, and in gray the packets that are received as an input. And here we have them as hexadecimal because they are sent as a byte, and each byte is 8 bits, so each of these bytes is actually sending 8 bits, 8 clock pulses on the wire. But yeah, as you can see now, we get to see the direction. And also, an important thing, there is a send command immediately, which, let's say, flushes the buffer. This comes useful later. So, okay. After parsing the MPSSE layer, we get a bunch of bits. A bunch of bits that are sent and responses that are received. Sometimes the response is all zeros, and sometimes the response has clearly some kind of payload, but we have to figure out what all of these bits are telling us. So let's do some statistical analysis on the bits. So we can sort all of the messages, group them by their size. And here, for example, I sorted all messages that have this size, so don't know how many bits, and I grouped all of the ones that start with this sequence of bits, because these were very common, so I thought about starting with this. And what we immediately see is that some bit positions change more than others. Some bit positions are more correlated to others, so they don't change as much, or they change together with others. Some bit positions seem to change wildly, and in other words, they have high entropy, and they are the last 6 bits. So we know from before that this protocol uses CRC6, and of course, cyclic redundancy check code is going to have a higher entropy than the message. So we immediately get to figure out that the part with high entropy is the CRC6. And from this, we can also figure out what the CRC6 is computed over, because we know the polynomial already. I mean, there aren't really many possibilities of polynomials with only 6 bits, so we could have also done it without this information. So this blue part here is the part that the CRC6 is computed over. And you will notice that there is always a 1 before. Then there is this data, which is protected by CRC, and then there is the CRC. So let's try to understand it a little bit better. We have this green highlighted bit, which is the start bit. All messages that are sent have to end with a 0. If they don't end with a 0, they are padded with a 0. So this is why sometimes the messages are longer by 1 bit, because they always want to finish every message with a 0. And there can be several 0 bits at the beginning as a padding. This is because they want to align everything to a multiple of 8, so that they can send the messages as blocks of 8 bits, so bytes, which is easier to do on this MPSSE protocol. This also tells us that the 0 bit is like, we can just send 0 bits forever and nothing will happen. It is basically a padding bit. Nothing is on the wire. Messages always start with a 1. Okay. After this, what we can also see is a correlation between the message length and some of these bits. In particular, these bits that I highlighted in purple, they change with the length of the message. There is a correlation there, and therefore when you actually look at how they are encoded, you can see that they tell you the length of the blue part. So here we have 110000, and if you convert that binary to decimal, least significant bit first. This is a 3, and this is a 3-bit message. And this is true for all the others as well. So now we know the framing of the messages. We don't know the meaning yet, but at least we know the framing. We have, let's say, a header which contains a command type, which we don't know yet. Then we have the length, and then we have the argument, and then we have the CRC. Okay, now let's try to figure out what are the most common message sequences. Because remember from before, we are expecting to see the debug operations that we do in our IDE. We are expecting to see them on the wire somehow. And these are after some initialization, which has a lot of really wild messages that I still don't know what they mean, but let's say there is an initialization with a bunch of messages. Then the communication becomes more boring, and there are, let's say, 2 common message sequences. There is this one which has command 28, then 8, and then 10, and then a response comes. And then the other one is message 28, 8, 9. Then a payload is sent without CRC. This is the only message that doesn't have a CRC for some reason. And then command 8. And you can already imagine what they might mean, because this one has a response and this one doesn't. But let's see. So command 10 here, which has a response, is a read command. This is a very useful command. It just reads whichever address you ask it to read, and for how much data length it will read, as much data length as you tell it to. The encoding is such that the length is sent first and then the address. For some reason, the length is always +1. Not sure why. So if I want to read 4 bytes, I have to say 5. But this is what I discovered. So, and yeah, after asking for this address, for example, which is the chip ID, I get this response here, this blue response here. And there was also another curious part here, which is I was asking for 4 bytes, but I was getting 8, plus some residual at the end, which I didn't really understand. But there is always this 8 bytes instead of 4. If I was asking for 12, I was getting 16. There is always 4 bytes extra. And after looking around at what these bytes are, I figured out that whenever I was reading a location in memory that was 0, I was getting this magic number here, that by just Googling it, I found that this is the CRC32 of 0. Of 4 bytes being 0. And therefore, it makes sense that they would send the CRC32 of whatever you read, just to make sure that the read was correct. The other message that we saw before, the other command that we saw before, is the write, the one that didn't have a response. This is also a little bit non-standard, because for some reason the data that is being sent, the payload data, is not protected by a CRC6 or a CRC32 or anything really. And this kind of makes sense because you tell it that you want to write, in this case 4 bytes at this address, and then you start streaming data. You might be streaming thousands of bytes in a sequence, and the processor can't be expected to perform a CRC of the whole thing before writing, because it will need to store everything in a buffer to do that, and there simply is no buffer here. We are performing very low layer operations. So the writes are not protected. And yeah. What happens, what we can do already with the write is that we can start writing to the debug status register. There is a register here which has these bits here. In particular, we have halt. And if we set 1-1 on the halt register here, yeah, we are stopping execution. So this is the equivalent when in your IDE you press the pause button on the top. This is what the hardware is sending. It's sending this halt execution message. This is just as an example. Yeah, and then, as I was mentioning before, there can be password protected OCD interfaces. This is pretty common. We still want to be able to uncensor the interface, unlock the interface to perform failure analysis after the device breaks, but we don't want the customer or a thief to be able to perform debug operations on the target. So let's try to figure out how the unlocking works. So first I tried to lock a newly purchased board with a known password using the proprietary tools, and then unlock it and record all of the USB transfers. And I'm trying to see which additional dep telegrams are sent whenever I have to unlock it compared to when I don't have to unlock it. And this, in this case, there is this command 8, which is sent with this specific argument, and then the 256-bit password, which is pretty secure. 256 is a lot. It is sent 32 bits at a time, again with command 8. So for example, and there must be a 4 appended for some reason. So for example, if I want to send a dead beef, I have to send this with a 4. This is what I observe from the capture. And actually referencing the manual, for some reason, this information is actually written in the manual. Everything else about the DAP protocol is not, but by searching this number here, they actually mention that this is the same number I saw here, right? By searching it in the manual, it tells us that during the boot process, to enable the debug system, we need to send this number to the COM data register. We don't know much about this, but at least we know that command 8, apparently it's writing into the COM data register. So at this point, what are we able to do with everything we reverse engineer up to now? Well, we can read and write 32-bit words to arbitrary addresses. They don't need to be 32-bit, but they need to be aligned to 32-bit boundaries. This is enough to dump all of the flash and the RAM if we have debug access. This allows us to write directly into RAM. As I showed before, this allows us to halt and resume execution of whatever program is running there. We can set the program counter and the other registers. This is actually very surprising. In every other protocol, in every other OCD protocol that I've seen in the past, normally the registers are manipulated by individual commands. However, in this case, there is a memory address where if we write to that memory address, we are actually manipulating the program counter of each individual core. So if I write to this address over the OCD interface, where the star is the number of the CPU core, I'm directly writing to the program counter. This is actually surprising because this means that there is much less complexity to this debug protocol than normal, and less messages as well. In the same way, we can set breakpoints again by writing in the right position in the RAM. We can set both breakpoints and memory breakpoints or watch points. Finally, not finally. We can write the flash. Now, writing the flash is actually a very slow operation. It's described in the command sequences chapter of the user manual of the processor. So this is how you will normally write the flash if you were writing a program for a TriCore processor. You just have to send a sequence of memory writes at arbitrary addresses to get words programmed or erased from flash. However, this is extremely slow because to just write one word, we have to send a sequence of like 8 words. And the speed at this point is already pretty slow. So normally to write the flash, what we do instead is we upload a small program that executes from RAM, and that program then copies another portion of RAM into flash. And then we just put the RAM, the flash that we want to program into the other portion of the RAM, and then that gets written. And then finally, we can unlock the DAP interfaces only if we know the correct password. Do we really need to know the correct password? Maybe, but more about that later. Now, at this point, the next step for me was to re-implement it with open source tools, because as I was saying before, the official tools are quite expensive, but they use chips such as these FTDI chip that are available also in open source hardware, such as the Tigard here. This is a board that you can use to pretty much debug anything. They are extremely useful, and it uses the same chip as the Mini Wiggler, so why can't I use it instead of the Mini Wiggler? Well, the hardware is a little bit different. It's simpler. There is no direction switch for switching the direction of the individual pins. Instead, we have a physical switch which shorts together the output and the input pin. Not really short. There is a resistor in the middle, but a small one. Yet, by reprogramming a bit by programming it a little bit with Python and everything, I was able to get this to work with both the development board and the actual ECU on a car. So yeah, we don't need to use expensive proprietary tools anymore. We can use this open source stuff. And finally, the software itself, I wrote it in Python with the PyFTDI module. In particular, this is important to use batch-based implementation, in the sense that we want to batch as many commands as we can together, and then just do the execution that we saw before, the execution on the MPSSE protocol once, because this gives us extremely deterministic timings. It is perfectly timed with the clock that we set on the device, and this allows us to do fault injection attacks. I'm going to just have a quick demo. If you can switch the source. So I'm gonna have a camera here. Hello. Here I have the development board. You can see it's running the default program, which shows the Infineon logo. Oops, what did I do here? Yeah. And then I'm gonna run a small script that I can show you the script later, but there is not much time. And everybody wants to go to lunch, so let's just run this program. And now you can see that I was able to replace the memory over this program and got the HackInBo logo instead to display, just as a display that we can actually do it. And I also wanted to show there is this ops parser which parses the operations. After I sniff them from USB, I can show exactly what operations are done from a USB trace. So in this case, we can see that this is a read from this address. It's reading these 4 bytes out. Yeah, this was just a quick demo to show that we can actually do this stuff reliably enough for a demo. You can now switch back to the presentation. Just a moment, okay. And yeah, as I was saying, with these deterministic timings, we can now perform fault injection attacks and side channel attacks. So we might not know the password to uncensor our debug interface, but we have the tools now to bypass it or maybe extract it. So here, what I was showing is that on the oscilloscope, the entire process of attempting a password only takes I don't know, maybe 6 milliseconds. We can actually skip some commands and make it even shorter. This means that, okay, it's a 256-bit password, so we cannot brute force it, even if it only takes 6 milliseconds to make one attempt. But this is fast enough that we can perform fault injection when the password is checked, or that we can try to do side channel attacks. So try to look at how much energy the processor is using when comparing the password, and try to see if we can figure out how many bits we got right and how many bits we got wrong. And if we have that information, even a 256-bit password can be cracked very quickly. And also, of course, now this might remove the need for using Windows or expensive tools for this processor, but this is just a side effect. Now, future work, what else can we do, can be done to continue? It will be interesting to figure out the remaining DAP commands. I reverse engineered a bunch of them that I didn't show here because I didn't want to make it too boring, but there are still telegrams that I have no idea what they mean. But it's not so important because they're not so useful unless they are a backdoor, I don't know. It would be nice to contribute this entire thing to OpenOCD. OpenOCD is this project that supports the debug protocols for a lot of microcontrollers, and I would like to contribute my findings to OpenOCD. The problem is it's quite difficult to add an entire new interface. Currently, OpenOCD supports SVD and JTAG as physical layers. This will require adding a whole new interface. It's a lot of work. I will try to do it. And finally, the other future work is test hardware attacks on this DAP interface. I already did some work there. I cannot publish, unfortunately, because of NDAs. But we can try 3 types of hardware attacks that I already explained. Either fault injection on the password entry, fault injection on reset when the sensor bit is enabled or loaded from configuration, or side channel analysis of the password entry. This is it. I will publish the code. It's not public yet. I will make it public later today. You can contact me and you can ask me any questions. Thank you for attending.
Thank you, Andrea. Enrico.
Thank you very much to Enrico Pozzobon.